היי אביב.
היי אלון, מה שלומך?
בסדר, יפה שיש לך לוח בבית.
כן, מצאנו אותו ברחוב.
רחוב. וואלה.
אבל נראה תקין. תקינו אותו. כן. שכחתי לעדכן אותך, אבל נראה... כן, א' הם שלחו, אבל גם בהמשך מסתבר שהם החליטו שכן. אז יש... דוחים את זה, דוחים את המדרשה עד... כן.
לא נורא, כאילו... בסדר, חופש מוקדם, מה לעשות?
מה זה?
אני אומר שיצאנו לחופש מוקדם יותר.
כן. בסדר.
כן, כן. אל תדאג, אני אעשה את ההרצאה הזאת מתישהו.
בסדר. אני לא דואג.
בעיה עם זום זה לא מוגדר מתי ארוחת צהריים.
איפה גיא, הוא לא מגיע?
אתה יודע? אחד ממנו צריך להחליף אותו. עוד מעט.
למישהו יש את הקבצי ג'אמבורד של השיעור שעבר? או שלא שמרתם?
נראה לי שאולי יש לי של שיעור שעבר, שנייה.
קבצי מה?
את הג'אמבורד, נכון? היה הרי הוא, כאילו היה את הרשימות שהוא כבר שם ישר לקוח.
הבנתי.
אז אם למישהו במקרה יש, זה יחסוך לי את הסיכום.
נראה.
בהקשר של גיא יש, אז אני יכול לבקש ממנו.
יש לי, אני חושב שזה של שבוע שעבר.
יש שם חבורה ברקע. הנה גיא.
היי חבר'ה.
מקסימום גם אחר כך. תודה.
מה המצב?
מה קורה גיא?
מעולה, מה איתכם?
טוב. תגיד, יש לך מקום של כל הקבצי ג'אמבורד כזה, שאולי אתה יכול...
מה זה אומר מקום של כל הקבצי?
כאילו, אני מניח שיש לך את זה בדרייב.
מה?
כאילו, קישורים אליהם, או משהו.
אני מניח שאפשר לאתר את זה. אני אשלח לכם.
סבבה. מה ששלחתי, אני חושב שזה של שבוע שעבר.
אתה שלחת עכשיו משהו? אני לא רואה, אוקיי.
זה אולי זה שנייה לפני שהצטרפת.
ג'אמבורד חדש, לא משנה. אני לא צריך את זה בשבוע שעבר, אבל תשלח לכולם, זה נחמד. מה זה כל הג'אמבורדים? היה כאילו אחד שהייתי חולה פעם, את עכשיו, כאילו את שבוע שעבר והיום, ויש שבוע הבא.
אוקיי. אז אולי, אז כנראה שזה זה.
אוקיי. רגע, אז אני רוצה שנייה לשלוח את הג'אמבורד שהיום אני אשתמש בו. כולם בריאים?
ברוך השם.
כן, טוב. מה איתך? כולם בריאים אצלך?
כן, כולם בריאים. אבל הם בבית, הבנות כרגע.
זהו, ביטלו את הגן או שסתם בגלל שהגננת חולה או משהו?
לא, אנחנו הפסקנו לשלוח לגן ביום רביעי, אבל... Okay, sorry for the Hebrew, Hannah. So I said that we stopped sending the girls to the daycares because we thought anyway there will be many quarantines this week, and we were right. because that just they we stopped sending them on Wednesday, and on Thursday in both daycares there was somebody that had COVID, so the only I mean, in both cases, both scenarios, they're not going to the daycare, but only now they can do other things instead of staying at home. So okay, anyway, so you have the Jamboard, right? And let me share the screen. Okay. Aviv, I see that you are here today.
I did the binge of all the lectures in the last 2 days. So yeah.
Awesome. Okay, so we are together. Nice. Okay, so a quick reminder to myself as well. So last time we ended up discussing about something we can do with a G C-star algebra A. So we can always consider the space of all compactly supported or finitely supported functions from G to A. And of course, G embeds in it, and also A. And we defined an involution and a product in a way that makes the action inner. Okay. So I didn't write now the definition of the involution and the product, but you can check it in the last Jamboard notes. But it doesn't matter somehow, because once you want to have this property, there's only one way in which you can define the product and the involution. So that's the way we define it. And it remained to decide how to complete this. Okay, if we want to get a C-star algebra, and we do, this is the so-called cross product. So today we will consider two ways in which we can complete it. One, the universal way. One, universal cross product. So, okay, so for that I need the following notion. So definition. A covariant representation, U pi H of a GC-star algebra A consists of a unitary representation of U of the group on H, a star representation pi of the C-star algebra on B of H. Well, you know, now the C-star algebras are always unitars, and by star representations I always mean unitar star representations, unitar star representation. I don't know if I need to mention this. Also, of course, yes, so for time maps, it's needless to say, and in such a way that the action becomes inner. Okay, such that so usually I will write a unitary representation as with sub index, because it's easier that way. So UT times pi A times UT star will be pi of T times A. Okay. Hi, Tamar. So for this is of course for every T and T, and A, T, and G, and A in A. And obviously, any covariant representation gives rise to a unital star representation, star homomorphism of from our star algebra to B of H, right? Because our algebra respects these relations, and conversely, unital star star representations of finitely supported functions on G arises this way. Right? So definition.
Not only this way. This gives rise to unital.
I'm saying that only this way, in some sense, right? Because inside our algebra we have this relation.
Okay. Yeah.
So if I somehow have a representation of okay, I'm saying star representation of a star algebra. I hope it's clear, because we never define. I think we never officially defined star representation on star algebras without saying sister. But of course, it just means an algebraic one. There is no. Okay. Also the non-algebraic one, we defined it algebraic, and we just verified it. It's continuously as well. But anyway, so I'm just saying if the relation is satisfied here, then it has to be satisfied in the image. So we're good to go. Okay. So definition: the full cross product, or sometimes it is called the universal cross product,
or maximal
cross product, is of a GC star algebra A, denoted by like the semi-direct product, and sometimes with a little f for standing full, sometimes with a little u or m to say universal or maximal. I would not give it a subscript to this notion. Is the completion is the completion of our star algebra with respect to the following. Well, I want to say norm, but I need you to catch me. I have this problem again. Okay. I don't know. I think I have a problem with the item. So this is defined to be the supremum over all representations pi from CCGA to B of H is star homomorphism. Again, by star homomorphism, I mean homomorphism that preserves the star operation as well. So I said the norm, but you should ask me, Guy, why is it a norm? Why do we have at least one faithful star homomorphism, right? Right, it's not clear.
Why faithful?
I want it to be a norm. I want to know that if that this is zero, if and only if x is zero.
Why even is it finite?
So I also want it. So okay, what I want to know is that this set is not empty somehow, and not only that it is not empty, that it contains something faithful, and then it will be a norm, right? So, but trust me, I mean, we're going to see it later. But we'll forget about it for a second. So let me write, we will see later. We will see later. There is faithful or such faithful star homomorphism. There is such a faithful star homomorphism pi. So this is a norm. Is a norm. But please remember that I owe you this. Okay. For now, we will continue and believe me that there is one. Okay. So this is the completion. So remark. I don't know if I need to say it, but let me say it. Since it is faithful, then I can embed this inside. I mean, it embeds naturally here, and this is in fact the closure of this guy with respect to this norm. By definition, I didn't say anything. And now I get an immediate corollary from the definition. Corollary from definition. For every covariant representation, U by H of a GC star algebra A there is a star homomorphism sigma from the cross product to B of H such that sigma of ATT, I think of it as a finite sum, is equal to pi of ATT, UT. Right? For all, so okay, I move to the next page. For all finite sums. So and we denote this map. We usually denote this map. We usually denote this star homo or star representation. Now it's a C-star algebra. I can write star representation by U times pi or something like this. So diagrammatically, we have something like this, right? We have A, and we have G, and we can embed A in A cross product G and also G, and we have a covariant representation pi of A to B of H, and we have and U, so covariant representation is both pi and U, right? So U is unitary representation and pi is star representation. And the theorem tells us, or the corollary, that by construction, in fact, we always have such a star representation, right?
Guy, can we look at this as kind of a Alvesson extension theorem? When the operator system is the finitely supported?
I don't know. I mean, I wouldn't say something like this. We don't have Alvesson's extension theorem. Okay, there is an extension here, right? But it's something else. It's more like I don't know, extending something dense, like extending I don't know, a continuous function on a dense set to its closure or something like this. Alvesson's extension is something else. It's something like which is more like Banach, right? And also the maps are in different category of UCP maps. Star homomorphism. It's a different phenomenon somehow. Okay, so that's the point, and we have this. So I hope you now understand what is the universal cross product or the full cross product, good. So you see, it knows everything about the action of G on A somehow, and maybe let's focus for a second on a very specific case. Definition: when A is just the complex numbers, and G acts on the complex numbers trivially. So it is a GC star algebra, right? We denote this cross product. We denote this cross product by C star of G. Well, it is a C star algebra containing G somehow, right? So somewhere it's minimal, and call it the full C star algebra. Full C star algebra. Full group C star algebra. Full group C star algebra. Or universal or maximal of G. The corollary says that, so what is a covariant representation in this case, where the C star algebra is just the complex numbers? Well, pi has to be unital, so it needs to take 1 to 1, so I don't care about it. And U is unitary representation. So the corollary just say that unitary representation, unitary representations of G gives rise to unital star representations of C star G, right? And of course, I always have the converse direction somehow, because I can reduce myself to the group and I'll get a unitary representation. Okay. So do you have any questions so far? So pedagogically speaking, probably maybe many people would say, okay, it's better to start from defining the group C star algebra and only then to define this, I don't know, A-valued group C star algebra, which is the cross product, but I mean, I think it's fine also to do it this way. Okay, so now let's turn to the second option of completing this algebra, this star algebra, the reduced one or the minimal one. So now choose faithful representation, unitary of course, representation of A in B of H. So I write this faithful unitary as saying I embed A inside, right? I can always think of A as sitting inside B of H, but I'm choosing such an embedding. Define a new star representation. Define star representation as follows. So I'm going to define pi from A to B of, what is the Hilbert space I'm going to put here? Well, there are many ways in which you can think about it. One way is to think about it as L2, little L2 of G, but H valued. If you know tensor product of Hilbert spaces, then this is also equal to H tensor L2 of G, which is also equal to just the direct sum of H with itself infinitely many times and closing it in the natural way. Okay, so So how do I define it? So let's denote, let's denote or using this equality, I mean, it's the same thing. So, but right now, let me think of it as if I'm denoting psi tensor delta t. I'm just denoting the, right, we have your sequences in L2 of GH. So it's the sequence that has psi on the T entry, and 0 elsewhere. So this, I'm thinking of it as a sequence in L2G, which is H valued for psi that is in H. Okay? Is this okay? Good. So now I need to define pi. So for every A in A, I define pi A to be pi A of psi tensor delta t is defined to be, well, I want to act by T inverse on A, apply this on psi. This is now something that sits inside A, and A acts on H, right? Because A is a sister algebra in B of A. So apply this on psi, okay, and stay in T, in the T entry. So another way to think about such a thing would be to, right, you can, again, as I said before, you can think of this guy, if you want, as a G by G matrices, right? Do you see it? You can think of L2 of G, comma H as G by G matrices where the entries are in B of H. Right? Because I'm acting on such things. So if you think of it like this, then pi takes A. So right, I can think of it as if pi taking A to the matrix. This is a G by G matrix. G by G matrix. I don't know how to write this, that, well, outside of the diagonal, it does nothing. So there is like a main diagonal here. And outside of the diagonal, it is 0, right? Because it takes delta t to delta t. And on the diagonal, it does something like this. I mean, on the EE entry, it will be A. On the TT entry, it will be T inverse of A, etc. So this is like the EE entry. How should I write this? EE is the trivial element of the group, right? And this is like the TT entry. Does this make sense? Okay, please stop me if not, because I want to construct something and somehow I want you to be able to view it in your mind. Of course, we can also only stay with the formal definition, and it's also okay. Everything will work. So now the point, now I'm going to, so we embedded A into this thing, into B of L2 of G, comma H. Now I want to embed G, but I want to do it in a way that will be a covariant representation, that will make the action inner. Okay, so what's going to be the next embedding now? So what's going to be the embedding? It's going to be, so let me write consider maybe, and then I'll view it also matricially. Consider also one tensor lambda S, so lambda is the left regular representation. So what do I mean by the left regular representation? So do you all know what is the left regular representation? It just means that you take that on delta t, lambda s times delta t will be delta st. Let me write this. So this will take, okay, let me write this in this specific case. So psi tensor delta t will go to psi tensor delta st. So metricially, this will take S to what? Well, this is even more difficult to write. This is the matrix who has only ones on one of the not main diagonals. On the so I don't know, suppose this one is the diagonal through I guess SE. Please check me. I mean, I'm doing it from my mind, not from a book or anything like this. So here we'll have ones and zeros elsewhere. So this is unitary, right? If it was a finite matrix, then this could not be unitary. But since it is a two-sided infinite matrix, then it can be unitary, and it is unitary, right?
Could it be in the finite case, it's just a cyclic, like it is
Right.
unitary.
Say it again. In the finite case, it's what?
It should be unitary, no? Even if H is finite.
Yeah, there is a secondary diagonal here and maybe somewhere above.
Ah, you're saying, okay, right.
It's like a
You're
full shift
right.
matrix.
It should be, yes, you're right. Sorry. So it should be something like this, right? And more ones here. So this should be the diagonal that is through, I guess, E and S inverse, right? Something like this. No, that's the same diagonal. Diagonal through E and S inverse. No, but that's the case. I mean, I'm saying this diagonal is already here somehow, right? I mean, I don't need to. It should be. You're right. If it's finite, okay. So this picture that we give here is, of course, somehow heuristically, not officially. The thing is that if it was finite, then the diagonal that passes through E S inverse was sitting above somehow, right? But here, I mean, it's fine. So what happens if you try to imagine that you multiply these two matrices as I wrote them? So you take S and you take S inverse and you multiply them, then I think you will get the identity in both ways. Do you see it or not? Right, so you're trying to multiply this matrix and the one that goes with S inverse, and you will always meet when in the diagonal. So you'll get the identity. So if it works for S and S inverse, now converse the roles, and you get S inverse and S. Okay, so there is here something heuristically. So this heuristic mathematical view is good for an infinite, in the infinite case, for infinite groups, but you can imagine what happens in the finite case. Okay. So, but the point is that the action is inner. So let's verify this. I mean, I don't need to view it like this for what I'm about to write. I mean, if it's wrong, you can erase it. It's not important. What I just want to write is that this embedding of the group times pi a times the star of this acting on some psi tensor delta t, I can compute it, right? Without knowing even this matrix view. So okay, let's compute it. I mean, it's what? It's pi a of psi tensor delta S inverse T, which we know is 1 tensor lambda S of, we said, how do we act on a vector like this? We multiply by the inverse of T, and then leave everything as before. So I need to multiply things here by T inverse S, right? On A, on A on C, and leaves this like it were before. And this becomes so this becomes what? T inverse S A psi tensor delta T, which is exactly pi of SA of psi tensor delta T. Aha, right? So this shows that what? This shows that the action indeed becomes inner. So it is a covariant representation. Thus, 1 tensor lambda S, comma, pi, comma, L2 of GH is a covariant representation. Okay, so we get now a map from the full cross product into the Hilbert space, right? So we call it a regular representation. 1 tensor delta S times pi is called a regular representation because it depends on the H, on the way we embedded A into B of H, regular representation. And we think of it as acting on finitely supported functions over G. So definition, the reduced cross product of G on H of a G star algebra A, denoted by a semi-cross product G and the little r for reduced, is the norm closure of this map when applied to the finitely supported functions on G that are a value. This is, let's give it a different name now. Sigma. to sigma. So I restricted sigma, yes, but it's fine. Okay. And now you should catch me and say, but Guy, why did you write here that? Because somehow it seems that, right, there is I mean, it seems to be dependent on this initial embedding of A and B of H. Right? So this is something we still need to justify. This is something we need to justify, but let me just make two remarks. One, in particular, there exists a map. Okay, it's this map. I think of it as the image of this map somehow, from here to here, from the full cross product onto the reduced cross product. So the reduced cross product is in fact a quotient of the full cross product. So the latter is a quotient of the full cross product. Two, we have, I think now we have constructed a faithful star representation. So now we know that what I promised you before that will be a norm is a norm, right? Two, sigma is a faithful star homomorphism. So indeed, the norm from before is a norm. Three.
Hey, Guy?
Ken?
I think Alon started to ask it, and maybe Danny understand why, but also why the norm U is, we should to understand why it's finite, right? Why it's not, why the supremum of an element can't be infinite?
Okay, we know that star representations are a contraction, right?
If it is a C-star algebra.
If it is a C-star algebra. So you're saying there is an issue also of
why star representations are retroactively that they should be contractive, but
you're saying there might be a scenario in which the completion of this would not be a C-star algebra. In this case, you don't know a priori that even if we know that there are representations in this set, then maybe somehow the supremum will be infinite. Then maybe
this can be remedied. So, every element, so we need to show that this supremum is finite for every element individually, right? And it will be less than the L1 norm of the element.
That's completely right, but I was trying to look for a different argument, saying something like, in fact, in this scenario, we already know that such pi must be contractive, must be, and this is true. Well, okay. We also know posteriori it's true. I just wanted to say something like, well, so your argument was to use the L1 norm, right?
Alon? Because yeah, I mean, each X you can write as a finite combination of like delta G.
Yes.
Yeah, exactly. And just by the triangular inequality, it should be less than the sum of the norms of
You're completely right. And you
But
don't see any, okay.
Yeah,
So,
and you need to use the fact that, I mean, when you restrict pi to a representation of A and the unitary representation of G, then you know that the norm, that it's contractive and that G's and that T is unitary. So you have a trivial bound with your norms. Do you get what I'm saying?
so yeah, so I thought that due to this reason that you mentioned, yes, but I guess this is somehow equivalent. No, but here you don't say, you don't show it's contractive, you just say it for any X it's bounded.
I show it's bounded by the L1 norm.
By the L1
to say that the supernorm is fine.
Okay, so I guess that's a good explanation. I think also there is a way to justify this universally, but let's leave it for now. I mean, maybe we can think about it during the break or something. But Aviv, did you get to Alon's? So you can prove, I mean, it's not hard to show that for each fixed X, for each fixed element of this form, the norm will be bounded when you run over all representations, because well, you apply it eventually on I mean pi when restricted to the sister algebra is contractive. We know this, right? So, okay.
Guy, if you added the contraction condition in the definition,
what?
Why not add in the definition of the norm that pi is contractive?
I think you can. I mean, but I mean, it's redundant, and it can be easily justified. I mean, it doesn't. You don't need to. Yes. So once we justified it, let's say using Alon's way.
Contractive with respect to what?
Right. With respect
to defining the norm.
Right. You're right. You're right. You're right. Okay. So. Okay, so but let's move on. Just so 3, we still need to justify. We still need to justify the. I mean this the. Okay. So we'll do it in a minute. Okay. So maybe, yes, maybe, I don't know. Okay, maybe I'll edit in the break the comment that we had before, but okay. I want to move on. So, easy exercise or example or both, I guess. Example. If, again, if A is just complex numbers and G acting on them trivially, then L2 of G H becomes simply L2 of G, and our, how did we call it? I don't know, 1/10 delta S times pi becomes the good old regular representation, right? Lambda from G into L2 of G into L2 of G into B of L2 of G, sorry. And right, and CCG C is nothing but the group sister algebra, the group ring, and the reduced cost product, which is just the completion of G with respect to this norm of BL2G. is called the reduced group sister algebra of G, and denoted by C star sub R of G. So example, inside the example, sub-example, if G is the integers, then what do we get? Well, CZ, the product, you can go back and check how did we define it. The product on CCZC, which is again nothing but the group ring, is just a convolution, and it is commutative. So it is commutative. So it is commutative. Thus, the group sister algebra is commutative. And in fact, well, so you know it is C of something. Now think about the Fourier transform, and you'll find out that, well, that it needs to be C of the characters somehow, so of the torus. So maybe let me write this like this. So it's commutative, so we know it is something. And the Fourier transform, the Fourier, how do I write Fourier? Like this? Fourier? Yes, I'm not sure. Fourier transform identifies L2 of Z with big L2 of the circle, and this identification takes, and this identification takes C star R, a reduced C star algebra of the two multiplication operators. So maybe exercise. Now it's easy once I told you how exercise. Verify the reduced C star algebra of Z is in fact continuous functions over the circle. Okay. More generally, if you know what is a Pontryagin dual of a group, then you will get here the Pontryagin dual. Maybe let me just more generally, if G is abelian, so in some sense, you can think about the reduced sister algebra. So Pontry, how do you write Pontryagin? Help. Pontryagin like this?
Yes.
With capital P, probably. Pontryagin dual. So roughly, you can think about reduced sister algebra as a sort of a generalization of the Pontryagin duality. Okay, to the not necessarily commutative case. Yes.
What about the full sister algebra of this example?
So I didn't say, and this is more complicated, but let me not leave you unsatisfied and tell you the answer. The answer is going to be that whenever the group is amenable, then the reduced and full group sister algebras agree. Therefore, you can think about both as sort of generalization of the concept of Pontryagin duality to the non-abelian world. And it tells you that if the group is non-amenable, then somehow there is not a natural way, a unique natural way to create this Pontryagin duality. There are many ways. There are at least two ways, like a maximal one, a universal one, which is the full one, and a reduced one, which is the minimal one. And then there is a bunch of things between them somehow, which we didn't mention, but. Okay, so it tells you something like this. We can naturally extend the notion of Pontryagin duality to the amenable world, once you know this theorem that I said. And then we can also extend it to the non-amenable world, but then there are a whole bunch of options. Okay.
Guy, does it also work with finite groups that are not necessarily abelian? Is it also the Fourier transform of them?
So I don't know what is the Fourier transform of a non-abelian group, but
so it's just functions on the space of irreducible representations of the group.
Yes, it is. I mean, in this case, it's just a group algebra.
So yes.
This is the Artin-Wedderburn theorem.
Right, this will be the full group sister algebra, but I think yes, and it's somehow the yes, and that's the idea somehow of this notion. I think it comes from there. Okay. So I owe you. Don't forget that I owe you the thing with that. Why it is independent of the faithful representation of A inside the B of H. But for this, I don't have to do it, but I want to have to, because I will use it also elsewhere later, the next notations and notions. So some more notations. Consider the following. So I'm going to think of them right now as G-operator systems. I don't think I will need to think of them even as more than that, but okay, let's check. Right now, let's think about them as G-operator systems. So one, this will be MGA. What is MGA? MGA is going to be matrices. So I'm going to take matrices indexed by the group. So this is more or less what we tried to draw before, where XTS are in A. So if G was, I don't know, a group with n elements, then this is just Mn of A, right? Hence the notation. By the way, I invented this notation, so I don't know, maybe it exists somewhere else, but I didn't want to get into minimal tensor products or things like this, so I invented this notation. So just and these guys, these are the guys from the previous process. So I could have written here from MGA such that XTS are in A, so it is in MGA, and R inverse times XTS is X of TR SR. So this looks like matrices these matrices looks like this somehow. You have, I don't know, in this diagonal, you have A, and then if you go here, let's say this is the T entry, then you'll have here T inverse of A. And if you go to the S entry, you'll have S inverse of A, etc. And if you go to this diagonal, then maybe you have your B. And if you go to the T entry in this diagonal, then you maybe might have T inverse of B, etc. And so on, something like this.
Can you please write the equation a little larger? I'm not sure what is written. Ah, okay, thanks.
No, you're right, you're right. Let me. This is TR and SR. Is this okay? Or is it still too small? I mean, yes. So
it's okay. Thank you.
So these kind of metrics. I don't know how to call them. So and just maybe if somebody reads it, then this is. I don't think you'll find this notation. Let me call it not standard notation. Okay. So these are, of course, I mean, G acts on these. G acts on the. Yes.
So, Guy, just to make sure, the first one is not the minimal tensor product, right?
It is the special. Well, okay. Let's don't.
Never mind.
In the bracket,
Sorry.
what about the minimal tensor product?
Yes. Okay.
But
sorry.
If you choose right, it is a spatial tensor product with respect to something. Well, yes, you need to say with respect to what, but okay. Okay, let's skip this now. Anyway, so what is the action that I have here? So on these with so T times X is 1 tensor lambda T X 1 tensor lambda T star for X in MGA and T in G, right? I have this action where you already know what is 1 tensor lambda T in this, in B, right? They all live in this guy, so. And obviously, A reduced cross product with G, reduced, sits inside TGA. Now, what I want to claim, right? We wanted to show that the norm we defined on this guy is independent on the original representation of A inside B of H. So I'm claiming that this is true, in fact, for the norm on this guy, and therefore this will follow. So claim. We're now on page 5. The norm of a MGA is independent of the choice of the faithful star representation in B of H. Thus, also the definition of this is independent of this choice. Right, because I complete it, in fact, in MGA. The completion is taken in MGA. So proof, I mean, there's nothing to prove. I mean, it's easier than it looks like. It just boils down to the fact that we have a unique norm on M and A, which is something that we showed. The proof boils down to the uniqueness of the norm, of the sister norm on Mn of A. How come? Mn of A is n by n matrices over A, right? Well, let A be in A, in a, let's say MGA. Then for every F finite set in G, so I have again problems with the pen. Let PF be the projection, be the orthogonal projection onto you know what, onto the span of Xi tensor delta T. So everything, but I run only on T's that are in F. So right, this is a subspace of B of L2GH. Then PF of B of L2GH restricted to not restricted, let me write PF again, is of course isomorphic to MF of A. Thus, the norm, I mean, thus this norm PF something PF is independent of the choice of A and B of H, because this is something we showed or we discussed about it for finite dimensional for matrices, for finite matrices over A. But it's an easy exercise to show that the norm of A is nothing but the supremum over all PF A PF F by G finite. So A, so the norm of A is independent of the choice.
Guy?
Ken Yari? Yes.
We have any assumptions about G?
What?
We have any assumptions about G?
Discrete.
G is,
Discrete.
just discrete. Okay.
Well, I must say that when I wrote the notes to myself, I always imagined that G is infinite. And one should check that, I mean, if G is finite, maybe things, well, maybe you need to justify them separately. Maybe it will work itself, but at least when I write it, when I wrote this, I had in my mind that G is infinite, but I don't think.
So the last equality holds for any G, right? The norm of A is just the supremum of.
Right.
Okay.
Right. You run over all finite subset of G, so that's an easy exercise. Okay, this is on the one end. So good. So now we know that it is independent. But now I want to say something else. Again, people usually prove it only for the reduced cost product. I'm going to prove it to something bigger, which is this TGA that I define. So claim the map from TGA onto A that takes a matrix to the EE entry of it is a faithful GOCP projection. Well, when we think, well, I didn't say how do we think of A sitting inside TGA, but we think of A as sitting inside the reduced cross product that we said that it sits inside A. Right? So it's like dragon. In particular, and this is usually what people say, in particular, it induces a faithful GOCP projection on the reduced cross product. But I'm just telling it in fact comes from something bigger. So okay, showing it is GOCP is easy. I mean, the fact that it's projection is easy. The only problematic part is the faithfulness. But this is also easy. Why? Because if you start with XTS that is bigger than 0 and XEE is 0, so I'm going back to the previous slide. This is TG of A, right? This is TG of A. And this is the EE entry. So suppose that I'm telling you, do I have a, yes, I'm looking for something like this. Suppose that I know that this is 0. Ah, no, it kills everything. Why? Anyway, suppose that I know suppose that I know that A is 0. Then you agree that all of this diagonal has to be 0, right? But if all of this diagonal is 0 and this matrix is positive, then also this submatrix is positive, this one. But the diagonal of this 2 by 2 matrix is 0. So this must be 0. But if this must be 0, then all of this diagonal is 0. And also all of this diagonal will be 0. And then you go and continue like this. So everything will be 0. So it's faithful. Is it okay, or do you want me to repeat this? Let me say it again. So the GOCP projection just takes this matrix to A. So it kills everything and preserves A. I'm saying if it takes a positive matrix to 0, so it means that A is 0. If A is 0, then all of this diagonal is 0, because this diagonal is just the orbit of A. But if all the orbit of A is 0, all of this diagonal is 0, then consider this matrix. It needs to be positive because it's a compression of a positive matrix. But its diagonal, it's a 2 by 2 matrix, and its diagonal is 0, so these guys will be 0. But then all of these, their orbits will be 0, etc., and continue like this. So let's write something about this. So I don't know if so and X in it, then the main diagonal is 0, but then by compressing into a 2 by 2 matrix, sitting with the main diagonal, that I don't know how to write, that sits on the main diagonal. It doesn't matter where I put it, but as long as it sits on the main diagonal of XTS, איך אומרים, the diagonals from second order, the second order diagonals, I know, the second order diagonals are 0, 2. Continue. Similarly. And another claim I want to mention, and then we will take a break, that that we have from almost freely from definition. I just want to write it down. A claim. So if we have a GOCP between two G-sister algebras, then it gives rise, of course, to a GOCP phi G from mg of A to mg of B. This is what we had before with n by n matrices over G-sister algebras or operator systems, but now it's like infinite by infinite matrices. And so this is also GOCP. And one phi G maps Tg of A into Tg of B. Well, this is immediate. Phi G maps the reduced cross product of G into the reduced cross product of this guy. And also maybe just to mention it, it is UCIS if and only if phi is UCIS. Proof follows by definitions. There's nothing to check, in fact. After the break, I will discuss about, okay, so maybe I'll discuss about it after the break. So let's take a 15-minute break, or let's meet in a 3:15 again. So, okay. I will make some coffee and I'll be back for questions if you have.
Good.
Okay, so we're back. I just added a small remark with what we mentioned before, that I mean the supremum of that if there are such representation, then the supremum is non-empty. Then the supremum is finite. Okay, so now let us move to the next thing I wanted to do, which is, well, it is related, of course, to cross product. And this is a theorem called Fell's absorption principle. So Fell's absorption principle. And it says the following thing. So if the U IDA H is a covariant representation, so this is just a fancy way of saying that A sits in B of H, and the action of G on A is unitarily implemented, right? Then the covariant representation U tensor lambda, so this is a representation of G, a unitary representation of G. Identity of A tensor 1 on H tensor L2 of G, which you can think of as L2 G comma of H, but now we have this identification, is unitarily equivalent, to the regular representation. In particular, we have that sister algebra generated by U tensor lambda of G and A tensor 1 is the reduced cross product. So what do I mean by that? Well, the way you should think about it is as follows, right? We have the full cross product of A and G. On the one hand, we always have a map, right, that takes us into the reduced cross product, which is the sister algebra that is generated by right lambda of G and A. On the other hand, we have here a new specific sister algebra of this form that is generated by U tensor lambda for some U and nothing, and A tensor one, I mean one of whatever needs to be. So this was a covariant representation, so we had this map, right? Because it was a covariant representation. This map is the map we denoted by, I guess, U tensor lambda times IDA tensor 1 or something like that. So obviously, we always have such a map, because I mean, it's easy to define it because it's well defined. If I take just lambda g to I can always take lambda g to this thing. Yes, here I meant, sorry, here I meant of g. So we always have such a map because we can always send a lambda g, lambda t to u tensor lambda of t, something like this, and a to a, and with all the and do it for finite sums, and it will be well defined, because whenever the source will be 0, then the image will be 0 as well. So it will extend to a star representation. So this is something we can always do, but the theorem tells us that this will be in fact an isomorphism that is unitarily implemented. So in some sense, you can think of it as if the regular representation absorbs any other representation. That's the reason it is called Fell. Okay, Fell is the name of the guy that did this, but absorption principle. And it's really easy to prove it. I mean, there's nothing to prove here. Well, this is more or less always the case when somebody tells you that something is going to be unitarily equivalent, because you just need to say who is the unitarian. There's only one way to say who is the unitarian. So let U IDA H be a covariant map, and define U and define U on H tensor L to G by U of, I'm telling you what it does to psi tensor delta T. Well, it takes it into, well, the only thing I can do is to take it into UT psi tensor delta T. And easy to check that U of one tensor lambda S U star becomes US tensor lambda S, and U of this matrix where we have A, T inverse A, etc. on the diagonal. I mean, that's the embedding. That's the embedding of A in the in our picture. So if you do this U star, you just get A tensor 1. So we're done. So they're unitarily equivalent. So we're done. Okay, and I mean, there is nothing, I mean, oh, okay, yes, it looks more fancy than it sounds. Let me maybe just add that also this specific case where A is trivial is always interesting, as you probably noted. Example, if A is C and G acts on C trivially, then whenever we have a unitary, you know, from G into B of H, then it gives rise, of course, to a representation of the group, of the full group C-star algebra. And the theorem that just tells us again that we're in this situation, that on the one hand, we always have lambda that takes us to the reduced C-star algebra. On the other hand, we have here U tensor lambda that takes us to the C-star algebra generated by U tensor lambda of G and sits inside B of H. And the theorem tells us that here we have a unitarily equivalence. So this example is also sometimes people refer to it as Fell's absorption principle, okay? Although it's a private case of something more general. So again, also in this case, it's interesting to note that the regular representation absorbs any other representation. And in fact, philosophically speaking, there is something hidden here that we didn't mention, and I would like to mention now, that is called weak containment of representations. So do you have any questions? Was it too fast, this Phelps absorption principle? Do you want me to say a few more words about it, or can I move on? Concretely, I will need to use it next time, this principle, and I will explain when I use it. I'll explain exactly what do I do, so don't worry about it. But right now, I do want to discuss about weak containments. So weak containments. And this is something that, in fact, has nothing to do with groups or dynamics. Whenever I have a sister algebra A, I can consider the following idea. So let pi be a star representation, or be star representation, unital star representation, and also rho be another star representation. So be 2 unital star representation. We say that pi is weakly contained in rho if the kernel of rho is inside the kernel of pi. So whenever rho kills something, then pi kills it too. And we denote it like this. So it's a curly less than sign. There's in fact another way that I could have defined this weakly contained, and here is the, let me phrase it as a claim. Pi is weakly contained in rho if and only if, of course, this is the same thing, there exists unital star representation that take the sister algebra rho of A to the sister algebra pi of A. Do you guys see why these notions are equivalent? Do you want me to slow down? Am I going too fast?
Could you maybe explain?
Yes.
The last line of Phelps absorption principle? I couldn't exactly understand what you meant by. Okay, so you had this new covariant representation, and you're claiming they are unitarily equivalent, right?
Right.
And the last line you wrote, the guy for that.
In particular, we have that the sister algebras are isomorphic.
No, you said it is easy to check U and 1 tensor lambda S. You start. Why is this the isomorphic?
Why is this what we want to check?
Yeah. Yes. Sorry.
So we want to check.
What is the regular representation and what is the regular representation tensor?
That's the regular representation.
So by regular representation, you mean I should think of the.
We said it here, right? We fix a faithful choice, a faithful embedding of A and B of H, and then where did I write it? And then this is the so-called regular representation. So yeah. So I mean, okay. I applied it only.
Sorry, that was.
Again, say it again, Alon.
So you mean you're just thinking of gamma G as acting trivially in A, right? The regular representation I'm used to is like A equals C, right? Where where the action is trivial, and here you're saying
we took here an embedded. To make things easier, I already thought here that A sits inside B of H.
Right, but you're looking. But by regular representation, you mean the representation of G on L2GH, where G acts trivially on H, right? Or something like that.
Say it again. Again, what?
But when you think of one tensor lambda S,
yes,
you're saying that one tensor lambda S is the regular representation. What you're considering? What, right?
Right.
I'm just saying that regular representation, you mean here that G is represented as acting trivially on H, right? Like there's no, is that what you mean? I mean, what do you mean by regular representation here exactly? It's not that A equals C, right?
No, A is not.
Maybe I missed it.
No, A is not equal C here.
Okay.
So you're saying something here is not clear. I mean,
no, it's okay. I think I just
maybe I'm missing something, but I mean there are. So.
No, it's okay. I just had needed some more time to digest it. That's all.
Okay. I mean, yes, I agree. I mean, right. We've just learned cross products, and now I'm proving all this bunch of theorems about them. But the point is, don't worry about this false absorption principle. When I'll use it, I'll explain what I use exactly and what do we need exactly to know. Okay, so I will use it very concretely somehow. Okay, okay. But I do want to continue with the notion of weak containment. So I'm just saying. I mean, this is a very easy concept. This is a very easy concept, very fundamental one. In fact, it has to do nothing with sister algebras. It's something I could do with subspaces of operators, and people sometimes do it. So you take two subsets of operators, and you say that one is weakly contained in the other if the kernel of all of. Okay, so let's not talk too generally, but let's say if it is an image of a sister algebra, then if ker rho is inside ker pi, so if everything that rho kills, pi also kills. It should remind you the ideas of absolutely continuity of measures somehow. And of course, it is equivalent to say that we can find the unital star representation of rho A onto the sister algebra pi of A. How come? So maybe let's write a proof, although it is very easy, but I don't want you to lose me. I mean, so if you know this, then how do you define this theta? Define a theta of rho of A to be what? Well, the only thing you can do, define it to be pi of A. Why is this well defined? Because if rho of A is 0, then pi of A is 0, because the kernel of rho is in the kernel of pi. It is well defined. Since rho of A is equal to rho of A prime or 0, it doesn't matter, implies that pi of A is equal to 0. Right, so if rho of A is equal to rho of A prime, then pi of A will be equal to pi of A prime. And the fact is, and now everything is multiplicative, so of course it needs to be star representation. And of course, it is. Okay, and the other direction is similar. I mean, it is immediate. I don't know why I wrote the details, but just to make it clear. Okay. So okay. So now there's something that is not so immediate, but also not very difficult. Claim if for any psi in H, we have that the vector state associated with it, corresponding to pi, belongs to the weak star closure of the span of the vector states of rho, then pi is weakly contained in rho. And remark, the converse is also true. The converse is also true, but I don't think I will use it. But will not need it. But it is a good exercise if you want. A good exercise. Well, you need to know something. I think you need to know that the vector states are dense, but once you know it, it's easy. And it's also a good exercise to prove that vector states are dense.
The convex combination of the convex, right?
The span of them, I mean. Yes.
Ah, so that would imply it. Cool.
Yes. So if you want, you can do this exercise, but you don't have to. But proof of the claim is also not difficult. I mean, I don't know if I want to do it. The idea is that okay, let me maybe explain it. I mean, it's even easier. I mean, if you know that you can write this as a, or you can approximate this by a finite linear combination of these guys, then of course it means that, okay, let's write this. I mean, it's one line, I guess. So if, it's even easier than what I thought. If rho of A is 0, then by assumption, by the assumption, xi of eta A, psi will be 0 for every xi in H. So pi of A is 0. Sorry, I had something even more complicated in mind. It's one line, right? If rho of A is 0, then all the vector states it defines are 0. So, okay. So usually, if you are a group people, then you will see this thing as a definition of weak containment. Then so usually group people will say something like this: definition of group theorists. It will look like something like this. If pi from G of B to B of H and rho from G to B of K are unitary representations, we say that pi less than rho is weakly contained in rho. So they will say something like this. They will say something like if for every xi in H and for every finite set f in G and for every epsilon greater than 0, there are eta 1 until eta n in K such that for every t in F, the vector state xi minus the sum of eta I rho t eta I is less than epsilon. But we will simply say, I mean, this is for the group theorists, we will simply say if the correspond if pi, I don't know, if pi twiddle is less than rho twiddle, where pi twiddle is the corresponding representation of the sister algebra. Okay, I just wanted to write here how people usually refer to this, but I mean, if you know sister algebras, it's in some sense more immediate. Definition: if H is a subgroup of G, we can always consider lambda G mod H the following unitary representation. So lambda G mod H of T, what it does to a Dirac at the coset SH, it takes it to the coset TSH. And this is called sometimes a quasi-regular star, a quasi-regular representation. So claim if H is a amenable subgroup, then the quasi-regular representation of G mod H is weakly contained in the regular representation of G. Let's prove it. I'm going to prove it very concretely. I just want to let you know that there is also a very philosophically more, let's say, smarter way to do it with industrial representations, but I don't want to go into this direction right now. So let's do it concretely and feel it in our hands for a second, okay? So first note. So I'm going to prove the property of approximating vector states, okay? And this would imply that the weak containment. So first note that it suffices to approximate only vector states. I mean, only for vector states with xi that is finitely supported, with xi, right, in L2 of G mod H that is finitely supported. Why? Because if Xi is not finitely supported, then you can approximate Xi by norm with some Xi prime, which is finitely supported, right? As L2 sequences, you can approximate any L2 sequence with a finitely supported L2 sequence. And with 2 epsilon proof, this will show that the corresponding vector state will be close to the vector state of Xi prime, right? Okay, I will not write this, but I mean, it's easy, it's standard. Standard argument. Now I want you to go, yes?
This is not true if H is not an amenable subgroup?
So let's see what, no, in general, no, okay? And let's see where I'm going to use amenability. So, but wait a second, now, note that so if you want to think about it, think of the case that H is equal to G, and then answer to yourself. But because I think you know the answer, so that's the reason I'm telling you this. But in a minute, I'll tell everybody what happens in the case that H is equal to G.
Yes, okay, thank you.
Okay, so now know that for every T in G, now this is regardless of Xi, I'm just saying an easy computation. What is delta in the coset RH of lambda G mod H of T on delta on the coset SH? This is just delta RH, delta TSH, right? Which is 1 if R inverse TS is in H and 0 otherwise. Agree? I mean, they are the same coset, only in this scenario. On the other hand, for Fellner sequence, on the other hand, for Fellner sequence, Fn for H, we have that 1 over Fn to the half chi of Rfn lambda t, the usual regular representation of 1 over Fn to the half chi of Sfn is equal. So now, I mean, the previous one was in, right? It was in L2 of G mod H. Now I'm in L2 of G. So these are functions, finitely supported functions. So these are finitely supported functions because the Fn's are finite, and I get here Fn 1 over Fn times chi Rfn chi TSFN, which is equal to R inverse TSFN intersecting with Fn over Fn. This goes to what? As n goes to infinity? Well, if R inverse TS is in H, then it will go to 1 by amenability. This is the Fennel condition. And if it is not in H, then, well, of course, the R inverse TS of H intersecting with H will be empty. So this whole thing will be empty. So these are equal. So why do I say it? Now it's just a computation. Thus, if Xi, which I remind you is finitely supported, is something like S in F, alpha S, delta SH for F in G finite, then Well, you see what happens, right? I will write it, but I mean, now it's easy. Alpha R delta R H, lambda of G mod H, T of alpha S delta SH. This is the same Xi. I just write it once with R and once with H because I want to open everything. Anyway, okay, I will not even open. I will skip it. You know what happens. This will be just the limit by the previous computation. It will be the limit of. You need to open things to see it, but I'm skipping this detail. Alpha R. Maybe let me write it like this: alpha R over Fn to the half chi R Fn lambda T. This was G mod H, right? Of the same thing. Chi SFN. Okay, and then goes to infinity. So you open everything and then you use the previous computation, this computation, to show that each coefficient will go to such a coefficient, and the sum is a finite sum, so it will converge too. So this shows what we wanted to show. So corollary from this. The following are equivalent. 1, G is amenable. 2, the trivial representation is weakly contained in the regular representation. By 1, I just mean this representation that takes the whole group into 1. Of course, it's a unitary representation, right? 3, there exists, how do I call it? Maybe I should call it multiplicative linear functional. That's the terminology we used before. Pi from the reduced sister algebra into C. Sometimes people call to such a thing characters, right? I mean, multiplicative characters. So let's prove it. So 1 implies 2. Well, take the previous claim with G is equal to H. Right, the claim with G equal to H tells us that lambda of G mod G, well, G mod G is nothing. I mean, it just takes just the trivial representation. Then it will be weakly contained in lambda G. 2 implies 3. Well, well, to say it is weakly contained, we said before, it is equivalent to say that C star, right? That I can take the C star algebra generated by lambda G of G, and I can take the C star algebra generated by 1 of G, and there is a star representation like this, right? This is what we say before, that C star of pi of A, or pi of A, which was already C star algebra, it goes to rho of A. There is a star representation, but this is just C, and this is just C star reduced of G. And 3 implies 1. Well, let's do it in the next page because I don't have enough room. 3 implies 1. What is 3 implies 1? Well, we have now, right, star representation here. And this is, I can think of it as a subsister, as a subsister algebra of L2 of G by Alveson's extension theorem, or I don't know what. Yes, I think, or the fact you can extend states or whatever. Anyway, you can find here a UCP map. Let's call it phi. It won't be, of course, star representation, but it will be UCP map. So now think about phi restricted to L infinity of G as a map from L infinity of G into C. Then you got a UCP map. Now verify that because the action is inner, then so let me write it like this, thinking of L infinity of G as sitting in B of L2 of G, and multiplying the function T, multiplying the function in L infinity, so for F in L infinity, T times F is like, so what is T times F of S? Is like F of T inverse of S. But this is exactly as lambda S F, thinking of it as operator in L2 of G, lambda S inverse. Right, so phi of TF, so phi of TF is phi of lambda S F lambda S inverse. Fine, so what? But here's the point. Phi restricted to this is star representation. Namely, this guy is in the multiplicative domain of phi. But if it is in the multiplicative domain of phi, it means that we can take these guys outside, right? It is a bimodule map. But the lambda of S are in the multiplicative domain of phi. So this means that I can write phi of lambda S, phi of F, phi of lambda S inverse. But now we are in C, everything commutes. So these guys kill each other. So this is phi of F. So phi is invariant mean. So phi is GOCP. So G is amenable. Now, okay, so we now proved that there are two important characteristics or equivalent conditions of being amenable, that the regular representations contains the trivial representations, and that there exists a multiplicative linear functional on the reduced sister algebra. The missing part somehow in this theorem is to show that it is also equivalent to the nuclearity of the sister algebra. I think that tomorrow, or if not tomorrow, then the day after, I will publish the third homework sheet in which I will define nuclearity of sister algebras and of maps, and I will let you I will give you to prove a few things, and also I will give you to prove. Don't worry, it will be with like many items and with explanation. Now show this, now show that this guy will be a nuclear sister algebra if and only if G is amenable. Okay, so we will complete this picture. Our next goal, so are there any questions about what we did so far?
We already see here that if the maximal and reduced are equal, then it's amenable, right? But isn't the converse also?
No, but the kind of nuclearity I want.
Yes, I understand. No, that's it's a different question. It's unrelated to what you said.
Yes, okay.
I mean, asking, is it almost like direct why, if you are amenable, then the reduced
So
and
maximal. For discrete groups, yes.
Uh-huh.
It is true, but we're not going to show this.
Anyway, I just mean one of the implications is direct from what you did just now.
One of which implications is direct? The one that
if the maximal and the reduced are equal, then it's amenable.
Right. Okay. You're asking me? I know you.
No. Never mind.
Maybe I didn't.
Yeah. Okay. Never mind. Just sorry.
No, I mean.
Guy?
Ken, yeah, yes.
How do we know that the action or just lambda s is in the multiplicative domain?
Because phi is multiplicative on C-star, on the reduced C-star algebra of G. Because we started with a star representation, that's the whole point. And this lambda s sits, and this lambda s sits here. So they are in the multiplicative domain. Okay, my next goal is to show, maybe I should stop for a few minutes and just say the following thing. So you now see that the reduced group C-star algebra knows a lot of things or is related a lot to G. And one question that bothered people for a long time, for several decades, was to find a dynamical or intrinsic characterization of the case where the group G is where the reduced group C-star algebra is simple. So maybe I will just mention its definition. G is called C-star simple if the reduced group C-star algebra is simple. And I'm just saying that remark people have searched, maybe I should say had searched because it stopped, many decades for dynamical or intrinsic characterization of sister simple groups. The first example of a sister simple group, as far as I know, is that of the free group. So it is a paper of Powers from the 60s. I think not from the 60s, I think it's from 1960 exactly, or even 559 or something like this, where Powers show that the group, the free group F2 is sister simple. I will give you to show this again in this homework exercise that I'm writing. It will be a simple corollary of what we're going to do next time. I must ask you something. I mean, I will need to fully complete what I want to do. I will need an extra hour or so. So next meeting is our last meeting. On the other hand, we missed one meeting due to Hanukkah, but I don't want to have a whole like a new meeting unless this is something you want to. But I do want to ask if it is possible to have an extra hour next time, maybe even before, to start at let's say 12:45 or even 12:30, because maybe we take another break. Is there somebody here who is not okay with that, to start 12:30 next time? So we'll start 12:30, and we will try to finish before 4:15, but let's say until 4:15, okay? Itamar, Benny, Jonathan, I didn't see your, yes? Okay. Okay, so I think this is what we do. And now I must say also that there will be small places in which I need to add a few details without explaining everything. But I will explain what I'm doing, but I won't be able to. There will be 2 points in which I will need to take some well-known facts from von Neumann algebra theories, and I will explain them, but I will explain them ad hoc without doing the whole thing. Okay. So right now, my next goal, which I will start now and finish the next time, is to prove a very interesting and important containment that might look obvious, but it is highly non-trivial. And this is the following fact. Recall that we have the G-injective envelope of a G-sister algebra A. Now this is a G-sister algebra, right? And I can take the reduced cross product of G's with G. On the other hand, I could take the reduced cross product of A with G and take the injective envelope of this guy without not G-injective envelope, just injective envelope. A priori, there should be no relation between the two. It is highly non-trivial if there is any relation between the two, but apparently it is true that we have this containment. It is a subsister algebra, and it's not that easy to prove this containment. Okay. For that, I will first want to prove a claim about one of the spaces we mentioned before, which is T sub G of A, that we mentioned today. So let me, and we'll finish by this today. So let me set a few arrows and then to prove. Okay, so I will do it in the next page because I want the arrows to stay with me. Their notion, their definitions. So set kappa from A to L infinity of G of A be the map that maps A into, so what it does to T, this is something we already defined. Maybe I didn't give it the name kappa, or maybe I called it iota or something like that, but we did define it last time. Sigma from L infinity of G of A to mg of A is the map that takes a matrix, that takes a sequence AG, AT, T and G, to the matrix delta ST, Kronecker delta AS. And so this is just our, right? This is just a if you compose kappa, so kappa, so kappa, what I want to say, so sigma composed with kappa, right? It's just the usual good old embedding of A inside MGA, right? It takes A into this diagonal, right? That here we will have A, here we'll have T inverse of A, etc. and zeros elsewhere. And also, I want to define tau to be the map from mg of A into mg of L infinity of A of GA. And this will be defined by tau of a matrix AST. It will be the matrix, the matrix of sequences. The matrix of sequences, the sequence will be A, SR, TR. כאילו מורח את זה ימינה כזה. R and G. This is weird, right? But yes, but this is something I need for the following claim. So claim TGA is injective if and only if A is G-injective. So proof. Let's start with this direction. If we know that, okay, regardless of anything, we proved before, today, we proved that there is a faithful GUCP projection from TGA to A. Do you remember this? Today we proved, today we showed there exists a faithful GUCP projection from TG of A onto A. So in particular, this shows that A is injective, right? Because TGA is injective, so it is a, if you are a UCP projection of an injective guy, then you are injective. So A is injective. But this is not what we need. I need to show that A is G-injective. But the fact that A is injective implies that MGA is injective. But this implies MGA is injective. Why? Because recall that whenever we have a map, that if A is injective, then it means that I have a map phi from B of H onto A, right? A UCP map. But then I can lift it. To phi G from B of L to GH, or from M, which is MGB, which is MG B of H, onto MG of A. This is the last claim I wrote before the break. So MG of A is injective. But by assumption tau TGA is injective, so it means that and TGA sits inside, but TGA sits inside MGA and is injective. So it means that there exists psi, a UCP projection from MGA onto TGA. UCP projection. Because if you are injective and you're sitting in somebody big, if you are injective and you sit in somebody big that is injective, then such a map must exist. This is something we also showed. Good. So we have this map. And now I have here this map sigma from before. Let me write it in blue. Sigma. So this is psi, okay? This is psi. But we also have sigma that takes us from L infinity of GA. And we also have here the map that goes into A. And I claim that this composition I claim that this composition is a GOCP map. And this is easy to verify. The composition is GOCP. And if you go back to the very beginning of our previous meeting, then you will see that this is equivalent to say that A is G injective. Okay, so A is G injective. What about the converse? So I don't have enough room for the converse, but let me try. So the converse now we assume that A is G injective, but by the usual injectivity, since A is also injective, not just G injective, since A is injective, there exists UCP projection from B of H onto A, which we can lift to something, to a UCP map from mg of B of H onto mg of A, right? That this we can think of it as B of L to G of H. Now by the G injectivity of A, we have this map that I mentioned, phi, that goes from L infinity of G of A into A, GOCP projection. And now I compose the following maps. We have a map from mg of A onto mg of L infinity of GA. This is the map sigma that I wrote before. Now I have here the map phi sub G, which is this phi, but over matrices that goes to mg of A. And eventually at the end, we have this map that's everything. That's everything I want. I'm just claiming, this map, phi composed with sigma from MGA into MGA is a UCP, sorry. Oh, okay, we know it's a UCP, but it's a UCP projection onto TGOA. And this is just a computation. And this is just a computation. I will not write the details because we're out of time. And I mean, this is really just a computation. Just take a general element of TG of A. We know how these elements look like. Apply the maps and check that it is the identity on TG of A. Also take a general element in MG of A and check that it goes to TG of A. So we have two computations to make, and they are easy. You just need to, I mean, there are no tricks here anymore. You just need to write them and to verify that it satisfies the conditions of being inside TG of A. So, and I wrote them to myself and it works. I mean, it's really easy. So it's easy. I'm not writing the details. If you want, fill the details yourself. Okay. So next time I will continue from this point that TG of A is injective to prove. I mean, it won't be easy. We will need to work it out at the beginning, but to prove this fact, then we will start to speak about. We will start to speak about the paper of Archbold and Spielberg, which tells us things about topologically free actions on compact Hausdorff spaces, and we will end up with the result of Kennedy and Kalantar about the characterization of system simplicity, which is that the action on the Furstenberg boundary is topologically free. And in fact, this is equivalent to just being free. Good. So I hope you stay safe and sound and happy and healthy, and that we will meet next week for our final, unfortunately, only online meeting. Bye.
Yeah.
Guy.
Thank you.
ביי, תודה.
תודה רבה.
להתראות.